If we imagine the current animation as being at the atomic scale, as with an electron orbiting the nucleus of an atom, we may use quantum mechanics to understand the relationship of matter, energy and space that make up our micro-universe. However, if we imagine the animation as being at the scale of our solar system, as with a planet orbiting a star, we may use general relativity to understand the matter, energy, and space relationship that make up our macro-universe. Both quantum mechanics and general relativity work well to explain the scale at which they are applied. It's when the equations of one are applied to the other that it becomes obvious that something is missing. The inability to reconcile quantum physics with general relativity is one of the most profound and challenging problems in theoretical physics, often referred to as the problem of quantum gravity. Quantum physics and general relativity are the two pillars upon which modern physics stands, yet they operate under very different principles and are applicable in different regimes. Quantum physics, particularly quantum field theory, QFT, successfully describes three of the four fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. It excels at explaining phenomena at the smallest scales of the universe, like the behavior of atoms and subatomic particles, incorporating the principles of uncertainty and the quantization of fields. General relativity, on the other hand, is a theory of gravitation that describes the force of gravity as the curvature of spacetime caused by mass and energy. It provides incredibly accurate predictions for large-scale phenomena, such as the motion of planets, the dynamics of galaxies, and the structure of the universe itself. The core of the incompatibility between quantum physics and general relativity lies in their fundamentally different descriptions of the universe. Quantum mechanics is based on the concept of quantization and the probabilistic nature of phenomena. It uses a mathematical framework that involves wave functions and operators to describe the physical properties of particles. General relativity treats space-time as a smooth, continuous fabric that can be warped by mass and energy. Its equations are deterministic and geometric in nature, describing how objects move through curved space-time. The mathematical frameworks of quantum physics and general relativity are fundamentally different and difficult to reconcile. For instance, attempts to apply the principles of quantum mechanics to the gravitational field, as described by general relativity, lead to non-renormalizable infinities, meaning that the usual quantum field theory techniques for dealing with infinities do not work for gravity. In general relativity, time is a dimension that is intertwined with the three spatial dimensions, and its flow can vary depending on the gravitational field. In quantum mechanics, time is treated as an external parameter, not as an operator like other physical quantities. This difference complicates attempts to formulate a theory that includes both quantum mechanics and gravity. General relativity predicts singularities, points in space-time where curvature, and therefore gravity, becomes infinite, such as at the center of black holes or the Big Bang. Quantum mechanics, with its inherent uncertainty, struggles to deal with these singularities where physical quantities become undefined. Several theoretical frameworks have been proposed to unify quantum mechanics and general relativity, including string theory, which suggests that the fundamental constituents of the universe are not point particles but tiny, vibrating strings. It naturally incorporates gravity and has the potential to unify all fundamental forces but requires extra spatial dimensions and has yet to produce experimentally testable predictions. Another theoretical framework proposed for unification is loop quantum gravity, LQG, which attempts to quantize space-time itself, treating it as made of discrete loops. LQG directly tackles the problem of quantum gravity without requiring extra dimensions or altering the standard model particles, but still faces challenges in producing testable predictions and fully incorporating the other forces. The quest to reconcile these two foundational theories continues to be a central goal in theoretical physics, with the hope that a successful unification will lead to a deeper understanding of the universe at both the smallest and largest scales. With the current technological leaps being made by AI platforms such as ChatGPT, one might think that by training the AI on all of the equations of the standard model of physics, ChatGPT or other AI platforms could see obvious problems with the data and resolve the mathematical issues faced when attempting to unify quantum mechanics with relativity, whereby producing a general unified field theory. One problem that might arise in such an attempt is that it would take a lot of creative ability to make the intellectual leaps needed for unification if we have the AI working within an incomplete paradigm. To understand the steps needed to allow AI to help us find a unification theory, we must first ask ourselves such questions as what is space-time? What are the quantum mechanical interactions that provide the mechanism by which rulers contract and clocks slow when accelerating towards the speed of light? What is dark matter and dark energy? What is a singularity? Why do we always receive the same measured value for the speed of light within different inertial frames of reference? And how do virtual particles pop in and out of existence? In Newtonian physics, gravity is described by Newton's law of universal gravitation. This law posits that every mass in the universe attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This force acts instantaneously across any distance. Newtonian physics assumes that space is an absolute three-dimensional stage where all physical events occur, and time is an absolute uniform flow that proceeds independently of the events within it. Both space and time are considered to be fixed and immutable backgrounds against which physics happens. Within this framework, the motion of planets, moons, and other celestial bodies can be accurately described for many practical purposes. However, Newtonian physics cannot explain certain phenomena, such as the precession of Mercury's orbit, using its concept of gravity. Einstein improved upon Newtonian physics with relativity by giving the mechanism by which gravity operates. He also seemingly disproved absolute space and time by establishing the relativity of simultaneity, length contraction and time dilation of objects, or frames of reference moving at different velocities. But there's still the question of what is space-time for it to be able to warp, and what's going on at the quantum level within the atoms of a ruler and clock as they undergo Lorentz contraction and time dilation. We know from concepts such as the Casimir effect that there are no true voids in our universe, as even seemingly empty space is not devoid of energy. It is science's treatment of space as a void that creates the very barriers that prevent us from arising at a unification theory, even if we employ the help of the best AI available. We acknowledge space as an entity of sorts when we join it with time and allow it to warp to change the path of celestial bodies. But the missing piece of the puzzle is understanding the matter to space equivalence. We know from the famous E=mc2 equation that mass and energy are equivalent, but once again, we don't know the quantum mechanical mechanism of how they are equivalent. Science's treatment of matter, energy and space as different autonomous entities is inherently flawed, and creates a mathematical barrier in the equations that cause the need for such concepts as dark matter, dark energy or the cosmological constant, etc. By acknowledging that space is simply an unstructured, less dense area of matter, we then allow the effects of the field or space to be part of the equations. All that we need to do to create a paradigm in which we may arrive at a unification theory is to acknowledge a fundamental substance, which has the characteristics needed to internally form all states of matter within itself, from the most solid objects to the seeming void of space. There is no true separation of structure in such a paradigm, only more or less dense regions. Thus, there is no separation of quantities and values. We simply need a fundamental substance with the properties of self-affinity and absolute motion. We then see that at the absolute scale, energy is not required for motion, but is rather or observance of changes within the state of motion from random to uniform. The math of the Standard Model is our attempt at a numerical analog to the interactions of our universe. The Standard Model math is correct. It's our interpretation of the underlying framework of the universe that it is showing us that is flawed. Rather than imagining vast amounts of structured matter scattered through even more vast regions of a spatial vacuum, we should imagine that at the heart of existence is a substance that gives rise to structure and field alike. First, we'll acknowledge a cosmos outside of our universal volume of fundamental substance. We can imagine it as a void much like we think of space now, or we can imagine it as an ever larger field of fundamental substance. Now we can take the absolute observer position and view the universal volume of fundamental substance as having absolute linear motion through the cosmos. In doing so, there is no internal random motion, thus the universal volume is at its most condensed state, occupying the smallest area possible within the cosmos. We might think of this as the singularity of the Big Bang. and being as our current mathematical models are actually measuring states of absolute motion rather than matter, mass, energy, time, temperature, etc. We can now understand why the math points towards a singularity, as there is no internal time, temperature, or structure, as all absolute motion that would go into buildings such is now conserved externally to the volume in the form of linear motion of the fundamental substance through the cosmos. It's only after the state change that causes the expansion of the universal volume of fundamental substance that any internal measurements or values begin to apply, as temperature climbs above absolute zero and mass is less than infinite. As described by the Standard Model, in the first few seconds, spatial density of the universal volume of fundamental substance, or UVFS, was high enough that the first atomic structured matter began to form. As the UVFS further expanded, thus cooled, the spatial density reached a point where it was too low to further form structured matter within empty field. Fast forward and black holes, galaxies and planets form, and the process of stellar nucleosynthesis continues to create ever heavier elements as it processes the UVFS in an attempt to return to the original state of the UVFS. It's the dichotomy, or yin-yang, of the uniform motion versus random motion within the UVFS that gives rise to existence as we know it, as the unstructured fields we see as space expand ever further outward, while the galaxies cluster and eventually get absorbed by the black holes at their center. We can now understand that the singularity at the center of a black hole is merely a region of substance nearest the initial state of the UVFS. That is the most solidified region in our universe. It's the introduction of random motion within the UVFS that cancels the fundamental substance's property of self-affinity. As structural motions becomes more linearly uniform, self-affinity takes over and concepts such as thermodynamic entropy apply. We can't further represent a black hole mathematically because, once again, it's devoid of further internal random motion. Thus also temperature, time, and energy, which are merely the many ways we measure the state of random and uniform motion within a volume of fundamental substance. In this theory, Einstein's space-time is the fundamental substance itself. Light is a shift or displacement of the substance at the smallest quantum scale, or rather the smallest resolution at which motion can interact within the fundamental substance due to atomic interactions. Our perception of light is our perception of changes in spatial volumes of substance. We visually witness the fundamental substance daily and across countless miles filled with celestial bodies. The changes in motion state surrounding structured matter give rise to the four forces of physics, as we can imagine the motions of the field surrounding stars, affecting the path the planets and light take around them, which is the same interaction that happens at the smallest of scales as an electron orbits the nucleus of an atom. Other quantum mechanical aspects are answered also, as paired particles are still connected by way of the UVFS, and light can truly mimic a wave or particle. When we take into account aspects such as spin, we can imagine that electromagnetic effects such as charge, voltage, etc. arise as a consequence of the change of motion states of the UVFS at the smallest of scales. The four forces of physics are merely pseudo-forces that arise from the exact same interactions of fundamental substance taking place at ever larger scales, which now gives us a path to quantum gravity. We can now also imagine the interactions described by special relativity within this new paradigm, being as the absolute motion within a region is finite and conserved. Thus, all structured matter has a frequency and wavelength aspect, whereby the faster an object is linearly accelerated, more uniform motion is imparted on the object. Thus, reciprocally less random motion goes towards establishing the object's dimensions and ability to track time, that is, length contraction and time dilation. One of the predictions of this model not covered by special relativity is the concept that we can't accelerate a structured object, much larger than an atomic particle, anywhere near the speed of light. Not because of the infinite energy requirement found within the equations of special relativity, but because it is analogous to the fact that the object wouldn't be what it is at those speeds, as the larger the structure, the more information in the form of varying states of motion that it contains, thus the slower it must linearly propagate to retain its form. The Lorentz contraction would ultimately reach a point of structural radiation. Much like the electromagnetic spectrum, there's a spectrum of motion between the speed of light and absolute rest, and where a volume of structured fundamental substance falls on that scale determines the allowable state the structure can be in. This means as a massive object accelerates towards the speed of light while surrounded by unstructured field, that is space, and its absolute motions that make it up become more uniform and linear. The motions that go towards its structure will be radiated back to the unstructured field, as structured fundamental substance requires multi-directional motion to establish the chemical and atomic bonds and such that allow it to be. The speed of light, or c, is absolute linear motion, and the closer a structured region approaches it, the less perpendicular motion available to communicate to adjacent regions to maintain the structure. Meaning, the information of the structure is lost, radiated away as electromagnetic energy. If one were to travel fast enough to catch a beam of light, then they too would be light. We can think of the fundamental substance as internally continuous, rather than particulate. It's fluidic in nature in terms of its ability to have increasingly varying points and resolutions at which it moves, as after the initial state change, random motion continually cancelled out the volume's property of self-affinity, causing expansion of the volume. To further our absolute observer position and allow more insight, we can now inject Newton's notions of absolute time and space back into the paradigm. If we now imagine the cosmos, within which the universal volume of fundamental substance propagates and expands, as a static three-dimensional field of vibrating points, as if they were the pixels by which material reality is projected, then we can now imagine that the initial state of the UVFS was a state where it occupied a single point, thus it could move at the velocity of c across the cosmic grid, the same way a photon moves within our universal volume. By all likelihood, our universe was once the photon of a larger cosmic region through which it traveled. This state would go unchanged unless the UVFS collided with another volume in a 2C collision. This would cause a disruption of the surrounding points as the information of the interaction was transmitted in all directions. We can see this as though the UVFS is expanding, as it occupies an increasingly larger area of the cosmic grid, while internally creating its own grid or scale upon which internal motions will later build structures, transmit light, etc., in an effort to work out its overall state of motion as mass and energy are now processed in terms of information. Relativity would be the way we internally measure the interactions within the UVFS once it starts to expand, as we try to measure it with instruments subject to the same singular process, but externally within the cosmos, absolute time and space would rule. We don't have to take the UVFS to the external absolute viewpoint to understand the majority of physics, however. It may be beneficial if we wanted to study the model using more Newtonian-type mathematical concepts such as frequency and wavelength with the backdrop of absolute time and space, rather than the relativistic-type mathematical concepts required to describe the interactions of the universal volume of fundamental substance from within it. It also may be the key to providing the paradigm by which an advanced AI would now be able to make further mathematical analogs and predictions simply by us closing the loop left by the standard model way of thinking of space as a void. The mass-to-energy equivalence is only possible because of the more fundamental equivalence of matter and space and the conservation of absolute motion.